to graphs in certain ways. So I want to go ahead and run through some of these things. So basically, I want to kind of go through the idea of this definition, what we mean by an absolute maximum and an absolute minimum, and it's pretty clear what it is, I think. But the definition a lot of times is not so clear to students. So what we're basically doing, I'm going to go ahead and just look at a couple of diagrams to show you what we would have on this. So an absolute minimum and an absolute max, all that means is what is the absolute biggest function value on a certain interval? And there's nothing to that. Okay, if you look at this example right here, I'm giving you an interval 0 to 2. The absolute maximum is going to be the biggest value, right? The biggest high point there is. So what we would say is you have an absolute max at x equals 2, okay? And then you would say it's 4 at x equals 2 like that. And then that would be the idea, okay? All right. So the absolute minimum would be that you have 0 would be the value of that minimum at x equals 0. So that's the way I want you to state them, is give me the y value, but then say what the x value is. Okay, that's generally the way we do that. Okay. Now this one right here, the interval is all real numbers. So when we do all real numbers on this, does this one have an absolute max? If you're doing the parabola on all real numbers, does it have an absolute max? No, it doesn't have one. Does it have an absolute min? Yeah. Yes. Okay, so it does have an absolute min only like that. So all you're doing is you're just looking at where the high point is and where the low point in the graph is, essentially. And that's it. Okay? All right. Now, next thing I want to look at is just kind of talk through this definition just a little bit. And when we do this, what this is saying is an absolute max is going to basically just say that every other point is less than or equal to the function value that you find. So in words, what that's saying is an absolute max is some point that you found where every other point is has a value that's less than or equal to it, right? Does that make sense? And then an absolute minimum would be the opposite. It would be a point where it's always greater than or equal to every other point on there, right? That's the idea, okay? So that's what you'd end up having on there then, okay? Okay, so let's go ahead and let's get into kind of formalizing this a little bit. There's a couple of other things that you want to make sure you pay attention to that are picky details. Okay, if you had a situation with an open interval like this, that's not an absolute max. Okay, there is no absolute max in there because you have a bubble there. Okay, you will never reach a specific value. Does that make any sense? Okay, it's just because you're getting close to it, but you have a bubble there, so there is no max there. There's no absolute max. There's also no absolute min there for exactly the same reason. Okay, so if you had this situation, there would be no min, but there would be an absolute max. So you have to pay attention to your intervals and whether they're open or closed. Does that make sense? Okay, so there's little picky details that you have to pay attention to. Okay, so we're going to just kind of classify these a little bit, and we'll kind of begin to get into the calculus here a little bit today too. So absolute max on this one. So what we would say on this one is we're just going to name where the intervals are, or where these are. So that would be your absolute max. That would occur at x equals b, okay? We don't know what the y value is. It's not told in this. So we just say, okay, it happens at x equals b. Where's the absolute minimum on this problem? Which x value? C2, right. So that is your absolute min, like that. So that happens at x equals C2. That's all that is, okay? How about the next one? Where's the absolute max? Okay, at C. So we just say x equals C. Okay, where's the absolute min? There isn't one. Good. Okay, how come? Because of that. So you have to pay attention to that. Okay, all right. Okay, let's do a couple more of these, and we're going to kind of begin to get into what we do with the derivatives and stuff. Okay, Absolute max. What do you think on C? Does this have an absolute max? No, there is no high point because there's a bubble. It's open interval, so there would have none there. How about absolute min? Do you have one? Okay, that happens at A. So there's your min. There's your max. Okay, like that. So that's going to be at A. Yes?
Would it be okay under other circumstances to write that the limit was, or that the maximum was the limit as it approached that point? So in other words, in this one, the max is the limit is x superfluous c.
No, we don't use a limit on that. Okay, it's because we're talking about a point on the function, a specific value. There is no specific value on this function that would ever hit where that bubble is. Even though you're thinking about the limit correctly, right, there is no function value. You couldn't pinpoint down a specific x that would give you that y. You see what I mean?
Right, the limit.
Okay, so the limit doesn't really have anything to do with the max or min. That's why. Does that make sense?
Yeah.
Yeah, there is no x that will give you the y value where that bubble is. Okay, and your job is to figure out what that x is. There isn't one. Okay, that's the idea. Okay, so you'd have that at C. Okay, absolute max on this one. Where's the absolute max on this one?
A.
At A. It's just a dot. That's okay. Okay, so that would be at A. X equals A. And how about minimum?
C.
C. Good. Okay, it's a cusp. It's a sharp point. So we got x equals c like that. Okay, students usually have no problem with that. What do you think? Okay, just pay attention to the bubbles. Okay, that's kind of a key thing. Okay, question? Okay, everybody got any, okay, any questions?
X equals A on C is the absolute minimum.
Question C.
That's the max.
No, the minimum. Minimum on C.
Go to the left.
Oh, on C, on this example?
Yeah, just forgot to put the last bar on A.
Oh, the little thing right there. That's what I forgot. Right, okay. X equals A, thank you. Okay, all right. Okay, extreme value theorem. Okay, now what we do on this says if you have a function that's continuous on a closed interval, we've talked about what continuity is, on AB, then it must have an absolute max and it must have an absolute minimum on that interval. Okay, so here's the idea. It's actually very logical and very simple. Is if I have a continuous function, I'm going to draw a continuous function and I have a closed interval, it doesn't matter how I connect them. As long as it's continuous, does it make sense to you that you have to have an absolute max and you have to have an absolute min?
Yeah.
You have to, right?
Yes.
Okay, because I never lifted my pencil. But what if I did this? What if I did this? Something like that. Does it have a maximum or a minimum? No, because I threw an asymptote in there. So the idea is there's a break in the graph when you have a discontinuity that messes it up. Okay, that's the idea. Or you could even have something like this, closed interval like this, and then you could have a bubble and kind of go like that. Well, that doesn't have an absolute max, does it? So does that make sense? If it's continuous and closed, you have no choice. You have to have a max or min. Is that good? Okay. You won't come up with any situation that will be contrary to that theorem. That's why it's a theorem. Okay. So let's go through and look at some this. What we're going to do is locate max and min on this. This one's a continuous function. So it's going to have a max and min. So the absolute max occurs where? X equals A. But, okay, and the absolute min, where does that occur? X equals C. Good. Okay. So does it meet the value of the extreme value theorem? Well, what is it? Is it continuous? Yes. Is it closed? Yes. So the answer is yes. Therefore, it was forced to have that. Okay. Want to make sure you understand the theorem. Okay, does this have an absolute max? Yeah, it does. It's at x equals c. Does it have an absolute min? No. Okay, so what did not hold? There's actually two things that didn't hold. It's discontinuous, right? And it's not closed. So it does not follow that theorem. So basically, it's not continuous. Okay, and it's not a closed interval. Okay, and really what messed us up on that is the fact that it's not closed. Okay? So those conditions have to hold. Everybody understand that okay? Okay? Okay, now we're going to get into the idea of what a critical point is. Okay, and this is what you're going to be dealing with over and over again in chapter 4, is finding critical points. Then we do stuff with these critical points. So a critical point is going to be somewhere in the domain of the function, and it's going to be a place where one of two things happens. Either the derivative is equal to 0, or the derivative does not exist. Those are the two things that we have for critical points. Now, can you describe for me what you've learned? What is one place on a graph where the derivative is 0? What happens? Yeah, like a maximum, right? If you have a maximum, you have a horizontal tangent line, right? Or if you have a minimum, you have a horizontal tangent line, okay? And then other places, there's all kinds of things where the derivative doesn't exist. We talked about discontinuous. We also talked about sharp points, right? So critical points are identifying where it's 0 or where it doesn't exist, okay? That's what you're wanting to do, and that's what we're going to do a lot when we start working these problems out. Okay, so what we're going to do is we're going to look at finding an absolute extreme value. Now, I'm just going to go through the examples, and I'll be kind of going through that procedure. That mainly is going to help guide you through that. The first thing you always want to do is you want to find the critical points. That's always step one, okay? Then you evaluate the critical points at the end point of the interval. I'm giving you a closed interval because I got to follow the extreme value theorem. And then you just put them in order. Whatever the biggest is the absolute max. Whatever the smallest is the absolute min. So we're going to try to do this as much as we can without a calculator, but you can use a calculator to verify this stuff and to help you with some of the calculations. Okay, so what we have is we have a function, x squared minus 10. Is that continuous? It's a parabola, right? So it's continuous everywhere. Is that a closed interval? Yes. So that means we have the ability to find the absolute max and absolute min. So first thing you're going to do is you're going to find the critical points. Okay, the way you find the critical points is you take the first derivative of the function. So what's the derivative of that function? 2x. Okay, so we got that. Okay, then what you got to do is you got to figure out where is that 0 or where is it undefined. So if you want to figure out where f prime of x is equal to 0, you just set the derivative equal to 0. Okay? If you want to figure out where f prime of x does not exist, that's more knowledge. Okay? 2x always exists. There's no place, there's no number for x you could plug into that derivative and get something that's undefined, right? 2x is a line. Okay? It's always defined everywhere. Okay? So all you got to do to find the critical point then is you divide both sides by 2, so you get x equals 0. Step 1 complete. We have critical point. Okay? And it's always the same. Take derivative, set to 0, or figure out where the derivative is undefined. Everybody got that okay? Okay, derivative's 2x. Solve the equation 2x equals 0. Okay, step 2. You want to work with the endpoints. Don't forget the endpoints. You're just going to start evaluating stuff. You're going to evaluate the endpoints and the critical point. So what we're going to do is kind of do this. I'm going to do f of -2 because that's an endpoint of the interval I gave you. Then we're going to do f of the other endpoint is 3, and then we're going to do the critical point. So basically you've got the endpoints there, then you got the critical point there, and then you put them in order. Okay, now you plug into the function, not the derivative, because you're interested in what's happening on the function at these 3 points. And whichever's the biggest, that's our max. Whichever's the smallest, that's our min. So all we should have to do here is just go -2 to the second minus 10. So that's 4 minus 10, that's -6. Okay? We do f of 0. That's 0 squared minus 10. So that's -10. Okay, then we've got 3 squared minus 10. So that's 9 minus 10, so that's -1. Okay, everybody see what I'm doing? Okay, which number is the smallest? That's your minimum. Which one's the biggest? That's your max. Okay, that's it. The calculus figured out everything for us without doing any derivative on that. So what we would say on this when we put our answer together, the way I want you to write the answer is like this. You say you have an absolute min of -10 at x equals 0. Okay, so that's where your absolute minimum is. Then you say you have an absolute max of -1 at x is equal to 3. That's that. That's the answer to the problem. Okay? All right. Did I put a graph on your handout? I think I've been trying to do some of that to kind of help you visually see these. So really what we found is, here's your minimum. That's at the point 0, -10. And then your maximum was at 3, -1. So visually you can tell we're right, aren't we? Okay? That's the idea. Okay? So you can do these graphically super easy, but the way I want you to do this when you're doing your homework and stuff is look at your graphing calculator to verify and help you understand. Don't just get your calculator out and find, okay? Because you could do it and not know anything about calculus. Okay, now let's see. Let's look at some other examples. There's a lot of things that can happen on functions. So the first thing on this is you do have a closed interval. Okay, so I'm always going to give you a closed interval so that you can apply this extreme value theorem. And then this function is always defined. So this function is always continuous. And it's continuous on that interval. There's no value of x that would make that undefined. So the first thing you want to do is you want to find the critical points. You find the critical points, what do? Take the derivative, find where it's 0 or where it's undefined. So let's go ahead and let's get our derivative going here. Okay. Okay, how are you going to do this derivative? What rule applied? Power rule, chain rule, really, right. But the power rule is certainly a part of that. Okay, so you bring down the 4/3, then you have x plus 1, subtract 1 from it, and you should be able to do that in your head by now, hopefully. So that's 1/3. If you do the derivative of the inside part, it's 1, right? So you even overlook that. But that is the chain rule. You're also doing that. Okay, what's that?
1/2 instead of 1/3.
Oh, okay. Sometimes I say something and write the wrong thing. It's like my brain's got too many things going on at the same time or something. That's the excuse I'm going to give you. Anyway, okay? Okay, all right. So now what we're going to do is we're going to set this equal to 0, like that, and we're going to solve the equation, okay? And a lot of times, guys, you can do this in your head. You could solve this equation in your head. What is x? There's only one thing that'll make that 0. What is it? -1, exactly. Now, you can follow through steps, but I encourage you, anytime it's simple, do it in your head. Okay, I'm going to go ahead and take the steps on this that you would take. One way to do this is you could multiply by the reciprocal to get rid of that. And really, a 1/3 power is a cube root. So that's equal to 0. Okay, so we got that. Now it's like college algebra. How do you solve an equation if it has a radical in it? You get rid of the radical, exactly. You cube it. If it was a square root, you would square both sides. Okay, so you would go through and raise both sides to the 3rd power. You would end up with x plus 1 equals 0. So x is equal to -1. So that is your critical point like that. Okay. Now, the other thing is, don't forget, students a lot of times have a tendency to forget about thinking about when the derivative's undefined. And that's my derivative. That derivative is always defined. Okay, there's no value of x that would cause a 0 denominator or something weird to happen. Okay, you can basically take any number, add 1 to it, and then take its cube root. That's guaranteed. Okay, so now we're ready to go to step 2. So step 2, what we do is we need to look at the endpoints and the critical point, and we're going to evaluate the function. So we do f of the first endpoint, then I'm going to do the critical point, -1, then I'm going to do the endpoint like that. So the idea is evaluate the function and then put them in order. Okay, that's how you do that. Okay, so we're going to go back to the original problem now. We're going back to the function. So we're going to do -9 plus 1 to the 4/3. So we're going to work that out. Then we're going to work out -1 plus 1 to the 1/3. And then 7 plus 1 to the 1/3 like this. And I think the numbers work on this pretty easy, so you don't need a calculator. What's that? Oh, 4/3. Yeah, see, there I go again. 4/3, 4/3, 4/3. Okay, all right, we good now? Okay, so again, see what you're doing is you always work with the endpoints and the critical point, and you're seeing what the function values are. Okay, so this is actually -8 to the 4/3. I would hope a student wouldn't go looking for their calculator to finish this. Okay, let me show you something. You need to know what this is. First of all, if you have a 4/3 power, what it is it's the cube root of -8 all raised to the 4th. This problem is designed so you don't need your calculator, okay? You can check with your calculator. What is the cube root of -8? -2. Be careful, it's -2 because -2 times -2 times -2 is -8. So that's going to be -2 to the 4th, and that's 16, okay? All right, that's how you do that, okay? I want you to do that without a calculator. This one is now 0 to the 4/3. Well, that's 0. Or, you know, what it means is the cube root of 0 to the 4th. So that's 0, okay? Then the next one looks like it's 8 to the 4/3. So that's cube root of 8 to the 4th power, okay? That looks like cube root of 8 is 2, 2 to the 4th is 16. Okay, you guys follow the arithmetic? Okay. Okay, what did we find? What's the minimum, first of all? 0. Very clearly, that's the smallest. What's the max? It's a tie. Okay, which is okay. You can have this happening at 2 places. So you'd have a max, absolute max there. So you're just putting them in order. So then you're ready to write the answer. So you would say absolute minimum of 0. So you say the y value, and then you say at x equals -1. Okay, that's the critical point. That's what caused that minimum. Okay, then what you say is you say absolute max of 16. You just write that once, okay? And then you say at, there was 2 places where that happened, -9 and 7 like that. So that's the answer to the problem, okay? So really graphically what happens, I put this on the graphing calculator for you. So you have the point -1, 0 is your min, and then out here you have a point 7, 16, and over here you have a point -9, 16. So it's just a tie. That's how that goes, okay? Okay, so does everybody follow that fairly well? Okay, if you can do your derivative, now the derivatives are weird on these problems. Sometimes they're a little harder than this, but that's the basic idea of how you do this, okay, mechanically. And there's a lot of times in applications where you have a function and you want to know where it's the biggest and where it's the smallest. That's very common. Okay, let's do something with a trig function then. And same idea. We have a closed interval and you have a continuous function on that interval. Sine wave is continuous. So we're going to start by finding the critical points. So we want to go ahead and do that derivative. Okay, what's the derivative of sine 3x? Cosine 3x times 3. 3 cosine 3x. Okay? All right, yeah, so derivative of sine is cosine 3x, but by the chain rule, the derivative of 3x is 3. So you got to be sure you have that, okay? All right, so we have that. Now, what we're trying to do now is we're going to figure out where the derivative is 0 or where the derivative does not exist. Okay, first of all, does not exist. If you graphed 3 cosine 3x, would there be any bubbles and holes and asymptotes and crap like that? No, okay, it's continuous everywhere. So we don't have to worry about that, okay? What we do have to worry about is solving the equation 3 cosine of 3x equals 0. So now it's back into your trig background. So we got to figure out how we do this, okay? Now, what I'm going to do on this is I'm going to show you kind of the way that you would learn how to do this in trig. There's a temptation to just get your calculator and figure it out that way, but I don't want you to do that way. I want you to do the mathematics behind that. So what we typically do, if you were solving this equation, you could divide both sides by 3 to get cosine of 3x is equal to 0. Okay? What does that 3x do to the cosine wave, by the way, from trig? What did you learn? Right, exactly. Changes the period, right? So this has been changed. So the places on the unit circle where the cosines equal to 0 have also changed, okay? The way that we typically do this if you have a period change is do this. Go ahead and do this. Take the inverse cosine of both sides. Okay, this is something we cover a little bit of in trig, so it goes like this. And then you got to watch this real carefully, because this is the type of trig equation students forget the most when they're in calculus. So the left side is just 3x. That's why I did that. Okay, it undoes the operation. Now we're going to think about the unit circle and think about the inverse cosine of 0. Okay, and you're going to look at every place where this happens, not just within that domain or range of the inverse cosine. It happens 2 places. You have the point 0,1, so that's pi over 2, right? Another place it happens is at negative pi over 2, if you went this way, because you have the point 0, negative 1, okay? Now, ultimately, our job is to find where the cosine is 0 on that interval, okay? Now, we're not paying any attention to the fact that you hopefully remember from trig, the range of an inverse cosine is 0 to pi. But I'm looking everywhere because I'm solving an equation. That's why I'm doing this. So what we're going to do is we're going to write down 2 things. We're going to write down it's equal to pi over 2. Then we're going to say plus 2 pi k, because the period of a basic cosine is 2 pi. Okay, that's going to change though in just a minute. Okay, k is an integer. Okay, so k is an integer. You want to write that down. Then we're going to do this. 3x equals negative pi over 2 plus 2 pi k, where k is an integer. Okay, now the reason we're doing this is because that period is getting ready to change, because we're going to divide by 3, and that's going to change everything. Okay, so on a unit circle, we know the cosine is 0 at pi over 2 and negative pi over 2. Everybody with me there? That's getting ready to change because we're going to divide by 3. The 3 changed everything. So now, go ahead, let's actually just multiply by 1/3, both sides of this equation by 1/3. Okay, and then we'll do the same thing the other one. So that's going to cross that out. That's going to leave x. Now if you multiply this out, see I'm doing pi over 2 times 1/3, so what's that? Pi over 6. That's a magic number now, okay? And then this is going to change to 2 pi over 3k, where k is an integer, okay? We're going to do exactly the same thing over here. You're going to multiply both sides by 1/3. So you'd have 1/3 times 3x is equal to 1/3 times negative pi over 2 plus 1/3 times 2 pi k. That's going to cross that out. By the same logic, that's going to give x equals negative pi over 6 plus 2 pi over 3k. All right, now that is a problem that you learned in trig. Does that look familiar? Okay, I don't, we teach that. It's just something that tends to get forgotten by students a lot when you have that period change. So here's what you do now. You want to kind of look at if k is equal to 0, okay, what's happening on this? If k is equal to 0, then what do you get? You just get x equals pi over 6, right? So that is a critical point right there. That's a critical point. Okay, we got that. Okay, so we have that critical point now, at least one of them. Whoops. So that's a critical point. Then over here, if we let k be equal to 0, we have another critical point. So that's x equals negative pi over 6, like that. Now you could keep going on this. I'm not going to do that, but let me explain why. If you went to k equals 1, if k was 1, now you would have pi over 6 plus 2 pi over 3, right? Okay, you would get a common denominator, which is 6. Let me show you what would happen. You would have pi over 6 plus 4 pi over 6, which would be 5 pi over 6. And that's out of range, right? Okay, it's too big. Remember, we're only interested from negative pi over 4 to pi over 3. That's it. So the same thing would happen here if we let k equal 1. Does that make sense to everybody? See, trig, it's going to show up in calculus, so you got to work with trig equations. So all that work just gave us these two things. Okay, we got two critical points now. Okay, everybody with me there? Okay, and you can verify that. The graph I gave you, what would happen on this, if you graphed that on your calculator, you could verify that pi over 6 would be a critical point. Now, does that make sense to you guys that the derivative would be 0 there? Yeah, because you got a horizontal tangent line. Same thing would happen here at negative pi over 6. So you can look at your calculator and verify that if you want to. Okay, so now what I'm going to do is the same procedure to kind of put this together. So we're going to work with the endpoints. We're going to do f of negative pi over 4. Then we're going to do our critical points. And it doesn't matter what order you evaluate these things. I'm going to do the critical points and the endpoints. So I've got to figure out these things. Okay, so my endpoints are this and this. Those are my endpoints. And then these two things right here are my critical points. Okay? Now graphically, see, the thing is, the temptation is, okay, well, you can already tell graphically where the max and min is, right? But the point is, we're trying to learn the mathematics behind this. So we're going to go ahead and crunch this out. So we're doing the sine of 3x. So if we plug in 3x, we're really going to have negative 3 pi over 4. We'd have to look that up on a unit circle. Then we're going to do pi over 6. So we're doing, remember, we're doing sine of 3 times that. So that's negative 3 pi over 6. Then the next one is sine of 3 pi over 6. Doing 3x. And then the last one is the sine of 3 pi over 3. Of course, you're going to reduce those things anyway here. Okay? So then if you go through and start putting these things together now, okay, this right here is, I'm going to start down here. That's the sine of pi. And you can kind of think about a unit circle. When you're at pi, what's the sign? 0. Okay, so we have the sine of pi is equal to 0. Okay, like that. This one is really the sine of pi over 2. What's the sine of pi over 2? 1. Okay, y value. Okay, so we got that. This one is really the sine of negative pi over 2. So what's that? Negative 1. Okay, so we got that. And then the last one's negative 3 pi over 4. The way I look at this real quick is I know it's a negative angle. I just count out pi over 4s. Sometimes students haven't caught on to this in their trig class because I just go 0. That's 1 pi over 4, right? 2 pi over 4, right? 3 pi over 4. Pi over 4 is 45 degrees, right? So I just go 1, 2, 3 pi over 4. What is that point on the unit circle right there? There you go. It's root 2 over 2. So it's negative root 2 over 2 and negative root 2 over 2. Okay, that's how I did that. So that means the sine of that is negative root 2 over 2, like that. Okay? Now, if you might not know what root 2 over 2 is, I don't know either. I just know that the square root of 2 is about 1.4. So I know that basically in this problem, this is your minimum, and then this is your maximum. Right there, you put them in order. That's some sort of a decimal right there. You could use your calculator to do that if you needed to. So that's it, problem done. So what we would have is we would say we have an absolute min of negative 1 at x equals negative pi over 6. And then we'd say we have an absolute max of 1 at x equals pi over 6, like that. Okay, I would consider that for probably most calculus students, that problem's a little more difficult than the first two. What do you think? It's just got more going on. It's just basically digging into your trig background a little bit. So you got to make sure that when you're solving a trig equation that you know how to do that. Because that to me is the big area of the problem right there, is how do you do that trig equation. Okay? Okay, any questions? Okay. Now, I want to do another one that's got an inverse trig function in it. Then I want to kind of go through to finish up with just a little bit of the local max and min here. Let me do one more problem like that, and then we'll finish up with talking about the local min and max. Okay, so Okay, so this one we've got a closed interval, and we're going to go ahead and do find the critical points. Okay, so we're going to do a derivative. So one of the things you got to know on this is you got to know the formula. We only learned this, I think, in the last class. So the derivative of the inverse cosine, have you got that down yet? Some of you do. -1 over square root of 1 minus x squared. You need to get that down, okay, before we get into that next test, okay? I want you to know inverse sine, inverse cosine, inverse tangent, inverse cotangent. Those are the four. Okay, so we go ahead and do our derivative. So f prime of x is going to be 2x. And then the derivative of the inverse cosine we learned is -1 over square root of 1 minus x squared, like that. Okay, so now we're going to think about the critical points and what's happening then in the problem. Okay, so what you do is you're going to set the first derivative equal to 0, and you're also going to think about if that's not defined somewhere. And you do have a place where this derivative does not exist on this, so we'll think about that in just a minute. So let's go ahead and take our derivative, 2x minus 1 over the square root of 1 minus x squared equals 0. One of the things I find in Chapter 4 where students a lot of times struggle a little bit is you start solving equations. Maybe you haven't seen some of these before, but this is a radical equation. That's what I see. So what I'm going to do is I'm going to get rid of, just move that to the other side, so I get 2x equals 1 over the square root of 1 minus x squared. And then really you can go ahead and just get rid of the radical right now. So how do you get rid of the radical? Square both sides, right. Okay, so you can do that now. And you got to do both sides to get rid of that radical. So that's the reason I'm going to do that then. So that's going to be something that's going to show up. You're going to have equations with radicals. So the left side is going to be 4x to the second. The right side is going to be 1 over 1 minus x to the second, like that. Okay. Now what I can do on this one is I'm going to write that down again. We have an equation with fractions. There's more than one way to approach this. So what I'm going to do is I'm just going to multiply both sides by 1 minus x squared. Okay, just to get rid of the fraction. You can also cross multiply. You can think of it that way if you want to. Okay, so I'm going to do that. So that's going to give 1 minus x squared times 4x to the second is equal to 1 when I do that then. Okay? Okay, everybody with me on the algebra? Okay, what do you think I should do next? Multiply it out. And I got to get one side equal to 0. Anytime your equation has exponents in it, you know, whole number exponents, you got to try to solve it by factoring. Okay, but the thing is, the right side has a 1 in it, okay, and that needs to be a 0. So we need to go ahead and multiply it out first. So that's 4x to the second. That's going to be minus 4x to the fourth, like s. Now we have a fourth power. And then we can go ahead and move the 1 to this side and set that equal to 0, like that, okay? So what I end up having here is I've got this, and I'm going to write this as negative 4x to the fourth plus 4x to the second minus 1 equals 0. So now the challenge becomes, is this something we can factor or not? Okay, so let's kind of look at this. The way I would look at this is I would do this kind of in my mind. I would go ahead and multiply both sides by like a -1, say like that. And that just makes the attempting the factoring to be a little bit easier. And this may factor, I don't know, we'll find out. So this is 4x to the fourth minus 4x to the second plus 1 is equal to 0. Okay, does that look like it might factor? It kind of has the structure that it might, so let's try it and let's see what happens. So if we factor this, the first term, what are you going to use for the first term? 2x squared, 2x squared. That's all you can do, really. Okay, how about the last term? 1 and 1. Okay, so now if you look at this, see, that's going to be a 2x squared. That's also going to be a 2x squared. Is that something you can make add up to negative 4x squared? Yes. How? Negative, negative, there you go. Okay, so it did factor. Hallelujah. I was getting nervous there for a minute. Because if it wasn't, then you have to do what's called a quadratic reducible equation and go to the quadratic formula. Okay, which is kind of a bummer. Okay, so I've got that. So let's see. We're going to have 2x squared minus 1 equals 0. So we just set each factor equal to 0. Okay, and we only have to do one factor because they're the same. So this is going to be 2x squared equals 1. Then let's divide by 2, so let's get x squared equals 1/2, like that, okay? And then we'll do the square root of both sides. And then don't forget you're doing a plus or minus when you do that. So you have plus or minus, the square root of 1's 1, then you have radical 2. And you can rationalize that, put in a rationalized form if you want to, but you don't really have to. So I'm just going to write that as square root of 2 over 2. Those are two of our critical points then. So this is part of what you get into these problems is a lot of work in algebra. Okay, like I always say, that's the algebra part's the biggest part of calculus that you have to work on, in my opinion. So we got that. Okay, now the other thing is, before we start evaluating things, I want to look at f prime of x. Is there any place it does not exist? And the answer to that's yes. Let's kind of think about that a little bit. You could actually do this in your head. Okay, you have a fraction, right? Is there any numbers that you could plug in for x that would make that radical 0? 1 and negative 1, right? Everybody okay with that? Because you'd have 1 minus 1 squared is 0. 1 minus negative 1 squared is 0. So this thing does not exist at plus or minus 1, okay? Well, the thing is, what's the deal with plus or minus 1? There already are endpoints, okay? So those are critical points, but they're also endpoints. So what we're going to do to finish up the problem then is we're going to do these things. We're going to do the endpoints first, so we're going to do f of negative 1.
Oh, so is it when we're giving closed brackets, they're just saying on this interval, they're not really letting you know that it might be undefined there?
Now, the thing is, the function is defined at negative 1 and 1,
right.
okay? It's the derivative that's not. If you graphed the derivative, probably what would happen is you probably have this this vertical tangent line. It's hard to tell from my graph on here, but I think what happens is the graph I gave you guys, I think it kind of turns down like this at the end and turns up like that, I think. I may be wrong about that, but something's going on that derivative. That's what I suspect's going on. So we're going to do f of negative 1, and then we're going to do f of 1, and then we also got to do our two critical points. So we do have two critical points. So let's see, our critical points were negative square root of 2 over 2 and positive square root of 2 over 2, and then we also have f of 1. Okay, so we need to go ahead and get all that put together. We'll try to do this without a calculator as much as we can. Okay, and there's a reason for that. You're also kind of going back and reviewing trig as you do this then. Okay? All right, everybody with me? The hardest part of the problem was solving that equation. Got endpoints, got two critical points. Okay, so we're going to do x squared plus inverse cosine of x. That's what we're going to do over and over again on these problems. And when we have that square root of 2 over 2, that's unit circle stuff, right? Okay, so let's go ahead and let's start with negative 1. Okay, well, negative 1 squared is 1 on a unit circle. Now, you have to think about this now. The inverse cosine is defined from 0 to pi only. You have to pay attention to that. We're not solving an equation. We're evaluating an expression. So from there to there, which value, which angle would have a cosine that's negative 1? Pi. What happens at pi? What's the point on the unit circle at pi? Negative 1, 0. Does everybody agree? Pi is where the cosine's negative 1. So that means you would have 1 plus pi. So that's what we have. I'm just going to leave it alone. We'll get a decimal if we need to here in a minute. Okay. Now we go to the next one. The next one we're going to do negative root 2 over 2 squared plus inverse cosine of negative root 2 over 2 like that. Okay. Well, what's going to be, what happens when you square the radical thing? What do you get? 2/4, right? Radical goes away, denominator's 4, so that is 2/4 or 1/2. And you can do that, if you can do that in your head, that's fine. So I'm just going to do that as 2/4, and remember the negative goes to positive, so that's going to go to 1/2. Okay, on a unit circle, from 0 to pi, does everybody understand why I'm saying 0 to pi? It's because of that range. There is a place where the cosine has the value negative root 2 over 2, root 2 over 2. You can look up the unit circle if you have to. It's quadrant 2. What is that angle? 3 pi over 4. It's 3 pi over 4. Now here's how I know that without having to go Google for a unit circle, okay, which is your goal, okay, is I know pi over 4 is where the root 2 over 2 comes on the unit circle. So I go 1 pi over 4, 2 pi over 4, 3 pi over 4. I count it out, okay? So that's going to be 3 pi over 4 like that, okay? Now we move to the next one. Let's see what we get here. So this is root 2 over 2 squared plus inverse cosine of root 2 over 2. Okay, same thing's going to happen. When you square this, you're going to get a half. Okay, where does the cosine take on the value of root 2 over 2? Pi over 4, right. Okay, it's quadrant 1, so that's pi over 4, like that. Okay, and then the last one we have f of 1, so we're going to have 1 to the second plus inverse cosine of 1, like that. Okay, on a unit circle, from 0 to 2 pi, where's the cosine equal to 1? That's 0. Remember, you have to pay attention to that range of the inverse cosine. Okay, so that would be 1 plus 0 like that. Now see, I didn't even touch a calculator. This problem was designed with that in mind. Okay, so we have that. So what we have is we've got 1 plus pi, 1/2 plus 3 pi, 1/2 plus pi over 4, and then we got, that's equal to 1 if you do that. Okay, well, you can use a calculator for decimal approximations if you want to on this. So one thing I know on this is that really is about 4.14, right? Because we know what pi is, okay? This one right here would be, that's like about 0.5, and then that's like about 12. See, pi is 3.14, so 3 times 3 is about 9, so that's somewhere around 9/4 or something like that. Okay, so that's smaller than that. And then this one is like 0.5, and then 3 divided by 4 is like about 0.75. I'm just using this to estimate. So now if you look at that, what do you think the minimum is?
1.
I'm pretty sure it's 1. Okay, so that's going to be my minimum right there. Okay, what's the biggest? 1 plus pi, or the 4.14. Okay, I'm pretty clear on that too. Okay, you can use a calculator to help, but it's also not bad to be able to estimate in your head. Think about stuff like this. Just use 3 for pi and use that to estimate. So now we got everything we need to know. So what we'd have is, for your result, you would have absolute max of 1 plus pi. And see, when you do this homework, I want that exact answer at x equals -1. Okay, that was an end point. And then you have an absolute min of 1 at x equals 1. And I think the graph that I put on your handout should basically show that okay. So you would end up having this point right here, if x is 1, y would be 1. That's your min. You can tell I put that in my calculator. I put the function in my calculator. And this point right here is -1 and 1 plus pi. And that's it. Okay? So again, what we're trying to do is get you to understand the mathematics behind this kind of stuff. The graph is supposed to open that up and help you make sense about what's going on. Okay? Okay, you got any questions? Now you're going to get into some messy algebra with equations and stuff on here. And I think we'll go ahead and just wrap up here today. Hey, we got spring break. My God, I'm going to let you out 7 minutes early. So now you can never say that he never lets us out early. This is a good stopping point. So we kind of got through the point that I wanted to get to anyway.